now that we've shuffled and split our data into training and test datasets, we can finally run our regression using scikit-learn. To do that, we're going to scroll back up and import this capability. So I'm going to say from sklearn dot linear underscore model import linear capital L regression capital R, all in one word. I'm going to hit Shift Enter on this cell, scroll back down where I left off, and then I'm going to create a regression object called regger. I'm going to set that equal to linear regression, parentheses at the end, and then I'm going to use this regression object and call the fit method on it. So regger dot fit parentheses, and now what do I add between these parentheses? What do I give as an argument to our fit method? The data that we should supply is our training data sets, right? So x underscore train being the training features and y underscore train being the training target values. And hitting Shift Enter on this will train our model. Great, but we don't see any output on the thetas that we've just estimated. And also, we don't even know how well this model fits our data. Now, before printing out these values, before printing out the values of our theta parameters, let's make some predictions on what we expect to see. Making these predictions is a very important step because it provides a sense check on what the computer is going to spit out to us. We should never blindly trust the numbers that we get back. That's how silly mistakes are made. Besides, we've done all this data exploration work up until now, and we can use the knowledge that we gained to make some predictions. For example, we've used Seaborn's pair plot to run individual regressions against our target prices. Also, we've created this wonderful correlation matrix to show the correlations of the individual features with our target. We know which correlations were positive and which correlations were negative. So, given that this is how our model looks like, let's make some predictions on the signs of the coefficients. Let's predict what kind of signs we're going to see on these theta parameters. So get out a piece of paper and write down if you expect the theta parameter for Rm to be positive or negative. And then do the same thing for NOx, PT ratio, crime, distance, and LSTAT. Did you pause the video and write this down? There's actually one more prediction that we said we'd make. Remember how a few lessons ago I asked you if you thought that being next to the Charles River was a good thing for property prices or a bad thing? Well, now it's time to also add your prediction to the sign of the Chaz dummy variable as well. Okay, so here's the solution to this challenge. I'm going to print out the value of our intercept, and it's going to be regger.intercept underscore, and then I'm going to print out the values of all the coefficients. And to format these values nicely, I'm going to actually put them in a data frame. So I'm going to say PD pandas, right? Dot data frame, capital D, capital F, parentheses, and then a first argument is our data that we're going to supply. And these are the coefficients, which we can find under regger.coef underscore. The second argument that we're going to supply is called index. So index equals, and then what we're going to supply as an index are the column names. So x underscore train dot columns. Yeah. So these are the column names. That way we can have the names of the coefficients next to the values. Let me show you what this looks like. Voila. We get something like this. We get our intercept printed here, and we get the name and the value of the different coefficients. Now, I'm going to come back up here into the code where I'm creating our data frame, and I'm going to specify a third argument called columns. Yeah, and I'm going to set that equal to square brackets and then single quotes coef. And when I hit Shift Enter now, you'll see this little 0 here, this little lack of a column name changed to the value coef. So columns equals, and then a list of one value, namely the string coef, will add a column name to our data frame here. All right, so we've got our results. How do they stack up to your predictions? Remember, we're just looking at the sign of the coefficients here for now. Are the actual coefficients positive or negative according to our model? Did you predict the right sign for the coefficients? Because what we see here is that more crime is bad for house prices, and also more pollution is bad for house prices. More rooms, on the other hand, is good for house prices. It's a positive coefficient. And more students in class is also a negative factor for the house prices, as is higher values for LSTAT. Now, looking at this, I think this is some really, really good news, because the signs of our coefficients passed our first sense check. All these signs that we've just talked about make sense logically. So the things that we would have expected to be bad for property prices from a logic point of view indeed have a negative coefficient associated with them. Oh, and do you remember how I asked you to make a prediction if living next to the Charles River was a good thing or not? Well, now we've got our answer. Looking at the sign on the Chaz variable, we can see that living next to the Charles River is indeed desirable, and the properties that are on the river are more expensive than those that are away from it, all else equal. In fact, we can put a number to it. Bostonians are willing to pay a premium for a property that is next to the river, and that premium is equal to about $2,000. Remember, Chaz only has the values 0 or 1. When Chaz is equal to 1, then it's next to the river, and 1 times approximately 2 is equal to 2, right? And since our target values, our property prices are in thousands, this translates into $2,000. So what we've just done in Jupyter Notebook is calculate all these theta parameters. Our model now looks like this. Using our training data, we've estimated all the values of these theta parameters. And the beautiful thing about this linear model is that all our coefficients have a very clear meaning. An increase in the number of rooms by 1 will increase the price of the property by $3,100. Our model is easy to understand and to interpret. It's the very opposite of a black box that just spits out an answer and we don't know where it came from.